number 12. Today we are going to see applications of Bernoulli's equation. Applications of Bernoulli's equation. See here, first we will see first application, speed of efflux. Speed of efflux. Here efflux means fluid outflow. Suppose fluid is in any container, then through the bottom it flows outside, we call it the efflux. Suppose you consider here, suppose a container. Suppose this is the container, and in this container suppose a fluid is placed, and suppose here we consider there is a small opening. This is the small opening, and through this small opening fluid comes out. Suppose here we consider this is the liquid is placed or fluid is placed. Now through this small opening it comes out. Suppose this is the flow of fluid in downward direction. This is the flow, that is flow in the downward direction. You can see different layers. Suppose these are the different layers. We have shown only 2 layers. Suppose P is the pressure here and A1 is the area of cross section. Here we can say that P0 is the pressure and A2 is the area of cross section, and suppose you can say this H is the height of liquid column. In your textbook here they have shown this side is closed, but if we show this side closed, then they totally closed, then this fluid does not comes in downward direction. Therefore we consider one correction in the textbook, that is here we consider this is the open container is open from the upper end. This is one correction. And if we have to show this container to be closed, then here we show one small opening. Through this opening air goes in the inside direction and fluid comes out. You choose anyone. That means you can show the totally open or you can show the closed and one opening there. Here suppose we consider rho is density of liquid. Rho is density of liquid. A1 and A2. These are the area of cross section at open end and bottom and top, such that A2 is very less than A1. A2 is very less than A1. V1, V2 velocities at top and bottom. P0 atmospheric pressure. H height of liquid in the container. Now here we write the Bernoulli equation that P0, PO, here P0 or half rho V1 square plus rho GH is equal to PO plus half rho V2 square, because at the bottom that potential energy is 0, height is 0, therefore potential is 0. And also from equation of continuity, suppose I will write this equation number 1, and from the equation of continuity we write V1 is equal to A2 upon A1 into V2. Suppose equation number 2. Now putting equation 2 in equation 1, we get half rho. Half rho. Now we consider here A2 upon A1 bracket square into V2 square plus rho GH is equal to half rho V2 square, because this 2 is here, P0 on both sides, we cancel this, and therefore it is not come here. Therefore, I will write here A2 upon A1 bracket square into V2 square is equal to 2GH is equal to, sorry, here is we consider plus is equal to V2 square. Throughout, this row is cancelled. Throughout, we can cancel this row. Therefore, I will write here 2GH is equal to V2 square minus A2 upon A1 bracket square into V2 square. Therefore, 2GH is equal to, I will write here 1 minus A2 upon A1 bracket square into V2 square, 2GH. And as A2 is very, very less than A1, therefore we cancel this term. And therefore I will write here, this is nearly equal to, we consider only 1, and therefore V2 square is equal to 2GH, and therefore V2 is equal to root 2GH. We consider, suppose this is equation number 3, this is equation number 4, and this equation 4 gives the speed of efflux. This is our first application, that is speed of efflux. Now we consider second application, B, Venturi tube. Venturi tube. Suppose you consider this is the diagram. Suppose this is a tube, and through this tube, suppose liquid flows. Suppose here area of cross section is same. Suppose I consider here this is one opening, and here liquid is placed in this tube, and suppose here, suppose this area of cross section will decrease at some point. Here suppose here is we decrease the area of cross section, tube becomes narrow. Again we consider one opening here, this is the narrow tube, and again suppose we consider the same area of cross section here. Okay, now suppose liquid flows through this tube. Now here suppose P1 is the pressure at this point, and we consider P2 is the pressure at this point. Here A1 is the area of cross section, here A2 is the area of cross section. Suppose here V1 is the velocity and V2 is the velocity here. V2 is the velocity at narrow region. Now suppose liquid level is here in this tube, and we consider here liquid level is here in this tube. That means here we consider this is the height difference. H is the height difference in both tubes. Venturi tube is used to measure the speed of flow of a liquid in a tube. It is a constriction in the tube. When fluid passes through the constriction, its speed increases and pressure decreases. We consider here A1, A2, these are the area of cross section. V1, V2, these are the velocities. P1, P2, these are the pressures. Now from the Bernoulli's equation, how I write here, that is P1 plus half rho V1 square is equal to P2 plus half rho V2 square. Here rho GH term, height is same throughout, therefore we cancel it, and therefore we write here P1 minus P2 is equal to half rho into V2 square minus V1 square. Suppose we consider this is the equation number 1. Now this is the pressure difference and H with the height. That means we can write here pressure difference P1 minus P2 is equal to, from this height difference we write here rho GH. Suppose this is equation number 2, this is equation number 1, and therefore I will write here that is rho GH is equal to half rho into V2 square minus V1 square. This rho gets cancelled. This rho gets cancelled, and therefore 2GH is equal to v2 square minus v1 square. We get, suppose, the equation number 3. We can measure, that is velocities. This is about the Venturi tube. Then we can see the next application. Suppose lifting of an aeroplane. Lifting of an aeroplane. Suppose you consider the shape of the aeroplane. That is, aeroplane is designed like this. That means, supposing that this is the imaginary shape of the aeroplane. Now, whenever aeroplane travels, then we consider here, suppose it moves, then air below, and we consider the upper. These air layers which are below and upper, they move like this. Now, whenever aeroplane runs on a runway, due to aerodynamic shape, here this shape is, we call it the aerodynamic shape. Aerodynamic shape. This shape of the aeroplane, we call it the aerodynamic shape of its wings. The streamlines of air are crowded above the wings. Here, see, these streamlines are crowded above the wings. Compresses to those below the wings. Thus, the air above the wings moves faster. This air above the wings moves faster than below the wings. And according to Bernoulli principle, the pressure above the wings decreases. Here, pressure decreases. Then, that is below the wings. And due to this pressure difference, here you see, here pressure is large, here pressure is small. Due to this pressure difference, an upward force exerts on that aeroplane, and whenever this force, upward force, becomes greater than the weight of the aeroplane, then that aeroplane takes off. This is the another one application of the Bernoulli principle, Bernoulli equation, lifting of aeroplane. We can see the next application, that is working of an atomizer. Working of an atomizer. See here, suppose you consider a simple diagram here. Suppose you consider piston is here. Suppose P be the piston and we consider C be the chamber. Now, at the one end of this chamber, we consider small opening. Suppose this is the small opening, and here we consider this is the tube which is dipped into the liquid. Suppose you consider this is the liquid. So we consider T be this the container. This is the block diagram of atomizer. The tube T is dipped in the liquid. Air is blown at high speed over the tip of this tube. Here you see, air is blown with high speed over the tip of this tube with the help of piston. We press this piston in this direction. In this cylinder, this air is blown out. The speed of air in creates low pressure over the tube. Here it creates a low pressure, due to which the liquid rises in this tube. Okay, this liquid rises into the tube and is then blown off with this very small droplets with expelled air. This blown off, we get shower. This is about the working of an atomizer. And last application, we will consider blowing of roofs by stormy wind. See here, suppose this is the block diagram of the house. Suppose this is the house. This is the house. Here we consider, suppose P be the pressure. This is the P0 be the pressure. Now, whenever stormy winds blows near to this roof, it causes a low pressure P above the roof, but the air below the roof is still at atmospheric pressure P0. So due to this pressure difference, the roof is lifted up. This roof is lifted up and it's then blown off by the wind. This is all about the applications of Bernoulli equation. We have completed this topic number 2. Thank you.